Okay, so to set up our discussion for gravitational potential energy, let's go back and look at two definitions from 298. So the first one's the definition for work. And we said that work is basically the integral from some initial position to some final position of force dotted in with our tiny little displacement. So what we're doing is we're adding in how the force projects onto our displacement as we go from some initial position to some final position. And then potential energy, the change in potential energy is defined to be equal to negative the work done by a conservative force. So to have a potential energy, you have to have a conservative force. In this case, the conservative force we have is the gravitational force. So talking about the change in the gravitational potential energy says we just need to put these two things together. And so we have negative, the integral from some initial position to some final position, the gravitational force dotted in with our little displacement. So if we want to start simple and think about a constant gravitational field which points downwards, i.e. we're talking about near the surface of the Earth. So our dot product, well, the only dr we care about, since the gravitational field points downward, the only piece of dr we're going to keep is the one that's vertical, so in this case that's dy. We'll move a little bit upwards in terms of dy. Our negative sign will be because our gravitational force points downwards, and so what you'll see is, hey, these two negative signs are going to cancel, negative, negative. That's going to leave me positive. M and G are both constants in what we've got here, so I can pull those out of the integral. So I'm left with just mg times the integral from some initial height to some final height, because the only thing I care about is what's going on vertically, of dy. So the integral where I just have my little dy term is just going to be delta y, and then when I plug in, I'm going to get final minus initial, so this is where I get my delta h from. And again, if I think about this, delta h can be both positive and negative. So if I'm at some higher final height than I was initial height, then final minus initial is positive. That means I went up, and that means I increased the gravitational potential energy. If, on the other hand, I went downwards, that means my final height is less than my initial height. Delta H is negative, and I decreased the gravitational potential energy. If you want to talk about the gravitational potential energy, well, because really the gravitational potential energy is defined in terms of its change. So whenever we're talking about the gravitational potential energy of a system, really what we have to mean is relative to some 0 point. And so if we have a constant gravitational field, one of the things that's nice about that is that we sort of have the luxury of picking the 0 point for the gravitational potential energy to be wherever we would like. And so then we can rewrite this equation and talk about the gravitational potential energy of our system as being plus or minus, and we'll come back to that in a second, m times g times h, where now all three of these things are defined to be positive quantities. So mass is always positive. This is the magnitude of the gravitational acceleration. So that's positive 9.8 meters per second squared. And then h is defined to be the distance above or below your 0 point. And so these three things are all going to be positive, which means whether our potential energy is positive or negative is going to come down to what sign we pick. And we're going to pick the positive sign if we're above the 0 point. We're going to pick the negative sign if we're below the 0 point. So the key thing to keep in mind here, because we're going to talk about the potential energy, and that's always, again, relative to where the potential energy is 0. All right, so let's talk about a more complicated situation. So if I've got a gravitational field that's not constant, but instead it's due to a point mass. So I know that that's a field that varies. The farther you go away from the point mass, the weaker the field's going to be in terms of its magnitude. And so here's a situation where to set up this integral. Again, I'm going to start with my mass. I'll pull it away, so I'll pull it in sort of the positive radial direction. The force is going to pull back in the negative radial direction. So when I think about the potential energy here between my two masses, well, let's think about what they want to do first. So I know they want to come together, right? My conservative force, the gravitational force, is attractive. It's trying to pull them towards each other. So they want to come together, which means that when I pull them apart, I'm making them do the opposite of what they want to do. So they want to come together, the gravitational force wants to do positive work and pull them together. So if I'm pulling them apart, that means I'm forcing the gravitational force to do negative work. Negative work times this minus sign means that the change in potential energy is going to be positive. And again, it's positive because I do the work. So I'm doing positive work to increase the potential energy between the two masses. And so when we go to think about what that means, it means that pulling mass apart, because we know that gravity is trying to pull them together, gravitational force is trying to pull our masses together, pulling them apart increases the potential energy. And so when we do this integral over here, we need to make sure that our answer is consistent with what we know is going on conceptually. And so I go ahead and plug in, well, I know the gravitational force, it radially is pointing in the negative direction, so positive R points to the right, it points to the left. There's a minus sign. Again, that minus sign is going to cancel with this one. Here's the magnitude, gm1m2 over r squared. That's the magnitude of the gravitational force here. And again, I'm moving some tiny little infinitesimal displacement in the positive radial direction. My minus signs are going to cancel. G is a constant, m1 and m2 are constants, and so all I'm left with is this integral from some initial position to some final radial position, and then I've got 1 over r squared dr. And again, when I do that integral, I know that's going to give me negative 1 over r that I need to evaluate from at my two endpoints, and so this is what I end up getting, that the change in the gravitational potential is equal to big G times the product of my masses still, times this term, 1 over the initial position minus 1 over the final. And if this looks backwards, it is backwards because of this minus sign. So this minus sign being here sort of flipped around, and the initial comes first and the final goes last. So again, let's make sure this makes sense. So if I'm pulling my mass, if I'm pulling M2 away, that means the final distance, its final distance to M1 is going to be larger than its initial distance. But if my final position, or if my final distance is larger, that means 1 over my final distance has got to be smaller than 1 over my initial distance. So sure enough, this term is positive, and I've increased the gravitational potential energy. So this is consistent with what we know conceptually is going on. Again, if we want to talk about the gravitational potential energy, we've got to define a 0 point. And from looking at this equation, it's fairly easy to see, well, the way to make this 0 is just to make r bigger and bigger and bigger. And so what we're going to do is we're basically going to set that the 0 point gravitational potential energy equals 0 at r initial equals infinity. And so we're going to be left with the expression that the gravitational potential energy, again, relative to the 0 point when they're infinitely far away from it, when my two masses are infinitely far away from each other, is going to be equal to negative gm1m2 over the distance between them. Okay, so R12 here is just the distance between R1 and R2. So again, this is a positive quantity. It's just the distance between them. My masses are both positive. G is just a positive number. All right, so let's think about what this means. So some important points about gravitational potential energy due to point masses. So thing number one is this expression is only valid for point masses. If you've got other things going on, then this one won't work. Now, just like with the shell theorem, we're going to be able to treat, or just like what we talked about with the shell theorem for gravitational fields, we're going to be able to treat most masses as point masses, and almost any problem we would work, at least that we're going to see in this class. So what are some important points that we need to keep in mind with this equation? Well, the first thing to notice is the gravitational potential energy is negative, it is never positive. It's 0 if my two masses are infinitely far apart, because that's sort of what we define the 0 point to be. But if they're not infinitely far apart, then the gravitational potential energy between those two masses is actually negative. So it's never positive. To increase the gravitational potential energy, then, means that I'm pulling my masses apart from each other And so my value for the gravitational potential energy is actually becoming less negative. So it's always negative. But to increase the potential energy doesn't mean that I have a positive potential energy. It means that my potential energy is less negative than it was before. Critically important, particularly when we start differentiating between potential energy and potential, but it's critically important to understand that the potential energy depends on two masses, like the gravitational force. It's also critically important to remember that the potential energy is a scalar. It's not a vector. There's no vector notation here. Direction doesn't matter in terms of what's going on in this problem. And then finally, we've been dealing with something that looks very similar to this, but now we've got just r in the denominator rather than r squared. So we'll often write this as m1, m2 over r, but that's clearly not m1, m2 over r squared. All right, so how are we going to use this in problems? Well, to calculate the gravitational potential energy of a mass in the presence of multiple point masses. So if I'm interested in the gravitational potential energy for mass 1, let's say. Well, what I need to notice is there's going to be an interaction with mass 2, there's going to be an interaction with mass 3, and so I just need to keep track of each pair. So I need to keep track of the gravitational potential energy between 1 and 2 and the gravitational potential energy between 1 and 3 if I want to get the total gravitational potential energy for mass 1. And so that just means I've got two terms here. If what I want to do is ask this an additional problem that says, well, what's the gravitational potential energy of my whole system? Well, now my system of 3 particles, I need to actually add up over all the possible pairs. So I've got 2 pairs so far, M1 and M2 and M1 and M3. What I'm leaving out is M2 and M3. So to deal with the system, then all I need to do to think about the system and the gravitational potential energy of the system is to add up all the possible pairs. So you notice that for my 3 particles, I can pair 1 and 2, I can pair 1 and 3, I can pair 2 and 3, and so I'm going to have 3 terms to calculate the gravitational potential energy of the system. And so what we'll concentrate on when we're working problems in class is how thinking about the gravitational potential energy and how it changes is related to the work required to move our particles around.